Hello students, I trust you're doing well. I wanted to spend some time just looking at the overall class, sort of like a roadmap. Several years ago we planned a short trip to the Grand Canyon and Zion and Bryce National Park, and my wife put together an agenda in about 2 or 3 days, and so we could look at that agenda and see what was going on. We could see our itinerary, and that's what I want to do with this class. I want to show you everything we're going to talk about in the class and sort of just give you a quick overview of what that looks like. And so I'm going to be in front of and behind the camera, and I'll be showing you the whiteboard and I'll also be showing you some of my notes. So we're going to have to do part 1 and part 2. So here's what part 1 looks like. Here's the subject matter that we are going to talk about. Okay, we're going to, if I were to do DC electronics in a nutshell, this is what it would look like. We would talk about the powers of 10, technical notation, color code, Ohm's law, Watt's law, and then we would get into circuitry or circuit analysis, specifically about series circuits, parallel circuits, series parallel circuits, and then troubleshooting amongst all those type of things. So that's sort of the roadmap. That's our itinerary for the next hour or so. Probably will spend maybe 15-20 minutes on this part 1 and then go to part 2. So let's take a look, and I'm going to try to set my camera up here for powers of 10. This is my classroom, and we're going to see if we can get this somewhat level. And we're going to look here just a little bit. And there we go. All right, so you should be able to see that. I've got a little pointer here. I'm going to use a yardstick to take a look at this. But what I wanted to take a look at is that you've seen this in various shapes and forms throughout your academic career in school, I'm sure, when we talked about metric prefixes and that type of thing. So powers of 10 are very important for a technician. So let's take a look. And I look at this as that all my numbers are based on the number 1, okay? So this is the number 1, and I'm talking about numbers that are larger than and smaller than 1. So when I look at this is that when I go in numbers, if I go in magnitudes of thousands or in multiples of 3, if you will, then the first number I get to is 1,000, and then another 1,000 would be 100,000 or a million. So there's 1,000, a million, a billion, and a trillion, okay? And then if I get smaller than that, I get to 1,000th, 1 millionth, 1 billionth, and 1 trillion. Now all these happen to be a derivative of a multiple of 3. So when I'm talking specifically about metric prefixes, all these prefixes are going to be multiples of 3. So it's a power of 10 raised to some power that's a multiple of 3. And those numbers that are above this number 1, which is my base number, are going to be larger than. These are larger numbers. And then I can get numbers that are smaller than. And when I look at that, numbers that are smaller than, that's what I'm looking at here. This is my minus 3, minus 6, minus 9, and minus 12. So each one of these ideas here is that when I take 10 to the minus 3, I simply can replace that with a symbol. And I've written the symbols out by the power of 10. If we go to numbers that are larger than 10, 10 to the third power, 10 to the third power is going to be a kilo. Okay, so a K represents a kilo, and then M represents a mega, and that's a million. So there's a mega. G represents a gig or a giga. Talk about a gigawatt or a gigawatt if you happen to be watching Back to the Future. And then, so that's going to be 10 to the 9 and 10 to the 12, which is a terawatt. So all these numbers are familiar. If you were looking at specifications for computers, that type of thing, then you're going to be dealing with these really large numbers. And instead of using all these zeros here, we're going to be using symbols, okay? So it's a lot easier to use these symbols right here than it is to use the actual number. And then again, when I'm looking at numbers smaller than 3, I'm dealing with 10 to the minus 3 is a milli, 10 to the minus 6 is a micro, 10 to the minus 9 is a nano, 10 to the minus 12 is a pico, okay? And all these numbers here are either bigger than or smaller than 1. That's my reference point. Where is the number 0? The number 0 is right down here at the bottom, okay? So 0 is down here. So all these numbers are still smaller, or still larger than 0, even though they may be infinitesimally small, a trillionth of whatever unit we're measuring. They are a power of 10. So there's an exercise that we'll do when we talk about this, and we'll do some technical notation. That's going to be a separate video, I think. On technical notation, it takes me a little more time to talk about that. The next thing I want to talk about will be the resistor color code. And that's going to be right here. I think we can see everything there. To move a few of my books, we'll take a look at that. And that's the resistor color code that we're looking at right there, okay? Now, the resistor color code is based on the 4-band color code system. And I'm going to see if I can find you a resistor here. I've got boxes of resistors. If I look at that, I've got a box of resistors. This is similar to what we use in class. Hopefully we can look at that there. So those are resistors that we look at in class. There's a couple of wires in there. And each one of these resistors has a color code on here. So these are, so let me just show you this one right here. And I'll come back to that in a minute. Can you see that? Let's see if I can focus in on that. There we go, see if it'll track it. That's probably about as close as we're going to get. So this resistor color code going from top to bottom is orange, 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 gold. So let's talk about what that means. If I look at this color code that's on the board here, I have a representative resistor here that we're looking at here. And this resistor has 4 resistive bands on there, 4 color bands on there, okay? And the way this is set up is that there are a digit 1 and digit 2. That's these first two bands here. Band 1 stands for digit 1. Band 2 stands for digit 2. And then the third band is the multiplier, okay? I'm going to times it by some number, okay? So that's my multiplier bands. So, and then the tolerance is going to talk about if you're doing manufacturing engineering stuff, you have to build something that's 5% plus or minus, then this tolerance code will give you the idea of the type of quality resistor that you would need in your setup. Now we use a color code here. There's various color codes within the electronic industry. And this is universal for resistor color codes here. And there are other types of resistors that have 5 bands, but we primarily, in our school, we primarily deal with a 4-band color code. So each one of these colors represent a number. So black, brown, red, orange, yellow, green, blue, violet, gray, and white. And that's sort of the spectrum of a rainbow. If you were to look at the colors of a rainbow, this is the way it would disperse. Red, orange, yellow, green, blue, and violet. So one shade darker than red we would consider brown, and one shade below that would be black. Likewise, if we go from violet and then go lighter to gray and even lighter to white. So that's sort of the reasoning or the logic behind the color code here. So I did show you this resistor, and that resistor was orange, orange, orange. So let's take a look at what that means. So if I have a resistor color code, and the first band is orange, and the second band is orange, and the third band is orange, and let's say the fourth band was gold, okay? So the first number would be 3. This is the first digit of my number. The second digit of that number would also be 3. And this orange means it's 10 raised to the 3rd power. But I simply say, how many zeros do you add? And that's going to be 0, 0, 0. And so this example would be 33 k ohms. Okay. And then this third band, when it's gold, is a tolerance of 5%. So that would be 33 k ohms plus or minus 5%. So usually we deal with gold and silver for tolerance bands, and this is when it's only in the 4th band. Gold is 5% and silver is 10%. When the multiplier, when gold or silver is in the 3rd band, this is the 4th band, When gold or silver is in the third band, it's a multiplier. And so gold becomes a multiplier of 0.1 and silver becomes a multiplier of 0.01. And you can remember that is that gold is going to be worth more than silver. So 0.1 is like a dime and 0.01 is like a penny. So you can remember those as multipliers. And so hopefully you'll get pretty extensive exercise in finding resistors and doing the resistor color code. The other thing I wanted to talk to you about would be Ohm's law. And Ohm's law has to deal with basically three things, and that's going to be voltage, amps, and ohms. And voltage, amps, and ohms, the easiest way to remember this is use these sort of these trigger words to understand what this is. Voltage would be a force. In other words, if we think about a water tower, and there's water there inside the tower, the gravity is going to cause a force on that water. It's going to create a pressure, and so we call that pressure force. So voltage is a pressure, is a force. I could have a 9-volt battery, and there's voltage there, but if it's not into a circuit, the voltage is there, but there's no current flowing because it's not attached to a circuit. So this idea of amps is the idea of current, and we call that flow. And then a buzzword for ohms would be the opposition of the flow of current. So there is a mathematical relationship with Ohm's law, and that's what I've written here. Volts, amps, ohms is what VA ohm stand. That omega sign, this funny looking horseshoe thing, this is a capital Greek letter for omega, and that's what we use for ohms. So these are sort of when I talk about Ohm's law, we can write that as an equation, and that equation is volts, amps, and ohms, and that's what we see here. And we can see also that I can take just sort of do a derivative of that little formula there, and I can solve for A for amps and ohms for, and these are what I'm going to use to calculate that. So let me get my tripod set up, and I do want to draw a picture here, okay? So I'm going to come all the way up here and do like that. And there's a unique relationship that we have with Ohm's law. And usually when we're looking at Ohm's law, we are thinking about what happens in the relationship of current, okay? So whenever I draw a graph, and that's what I'm going to draw here, is that we talk about whatever we measure is going to be on the y-axis, and we're going to say that we're going to measure amps. In this case, we're going to use voltage as a variable. This is what we change, and we're going to use ohms as a variable. So what I want you to do to understand, and we'll do this more when we get into laboratory, is that as I increase voltage, current will go up, and it goes up in a direction like that, the slope of the line. So the slope of the line is determined by the size of the resistor, okay? So the higher the resistor value, the longer the slope, and the smaller the resistor, the higher the slope, or the rise is faster and the fall is slower, okay? So let's take a look at amps and ohms. When I look at that, what happens is that when I increase ohms, is my amps go down, and it makes a little curve like this. And so when we get into Ohm's law and specifically talk about that phenomena, we have a term that we talk about, and we say that current is directly proportional to voltage. That means when volts goes up, amps goes up. And current is inversely proportional to resistance. So when ohms goes up, amps goes down. That's exactly what we see here. And then the last thing I wanted to talk to you about was watts. And when we look at this watts, let me back out of that there a little bit. When we specifically talk about watts, and I'll hold my tripod for now, is that when I think about watts or think about power, I'm asking myself what work is being done. And so when I think about watts, I think about work, what is being done. And if I take a light bulb and I screw it into an electrical outlet, it's taking that electrical energy and converting it into lumens or into light energy. But there's a way that we can mathematically talk about the relationship of watts, and that's simply here. Watts is equal to amps times volts, or amps is equal to watts divided by volts, or volts is equal to watts divided by amps. So if I have these three entities available to me, I can calculate the other two. So I can take the two variables I know and calculate the unknown. So that's our relationship we have with wattage. And then we'll talk later on about the power wheel. Let me see if I have a copy of that. And the power wheel is a way that we can take Ohm's law and Watt's law and combine it together. And when we combine it together, we can come up with 12 different formulas. And those 12 different formulas are called the power wheel. And I think I have a copy of the power wheel here. Let's see if I have one handy. If you look in the front of your lab book, I think that power wheel is available to you. There's some information in your book, in the front part of the book, page 1, I think. And it talks about the powers of 10, some of the Greek symbols we use and what we use them for. Also, some commonly used prefixes. And then sort of the relationship of the symbols and the unit of measure, and the symbols for the unit of measure when we're talking about electrical quantities, and that's there at the bottom. And I think I do have a power wheel. And let's see if I can pull that up here. But that's why it's important is that you get your lab book as soon as you are able to get that. What the lab book does is it allows you to go ahead and fill out that information. You have it all in one place. You can keep that information and have it readily accessible. Now, not all instructors will allow you to do this, but on my test, you're allowed to use your lab book. So I would also use it to take notes in. So you have that, all that information readily available. And we'll look at some of these other information, but this would be sort of the part 1 that we look at when we're looking at electronics in a nutshell. And it's going to be the first 4 of these that we talked about. We talked about powers of 10. We didn't really spend much time on technical notation. I'll do a separate video on there. We talked about color code a bit, Ohm's law, and Watt's law. So we're going to take a look at these next few things in our next video. And again, I hope to see you soon. Take care.